If you've ever dropped curry on a white shirt and tried to wash it, you've likely seen something strange happen. The moment soapy water hits the fabric, that bright yellow turmeric stain rapidly blooms into a deep red brown. That sudden shift is a visible signal, revealing the two opposing chemical categories that define these common materials: acids and bases. We encounter these extremes daily through the sour bite of a lemon or the slippery, bitter feel of soap. Identifying these chemicals by taste or touch is incredibly dangerous in a laboratory. To understand the substances around us, we have to rely on safer detection methods. This animation shows how natural indicators solve that problem. A simple liquid extracted from red cabbage acts like a chemical magnifying glass. Pour an acid in, and it shifts to bright pink. Introduce a base, and it turns a greenish yellow. But we aren't limited to using our eyes. Certain materials, known as olfactory indicators, let us detect a chemical's nature using our sense of smell. Take finely chopped onions, which have a sharp, unmistakable odor. Mix those onions with a strong basic solution, like sodium hydroxide, and that pungent smell vanishes. However, if you apply an acid to those same chopped onions, the strong odor remains completely unaffected. By observing these simple shifts in color and scent, we can safely detect chemical forces without ever putting a drop of an unknown substance on our tongues. Spotting acids and bases is one thing. Watching them physically tear into other materials shows us exactly how powerful they can be. Here, we drop solid zinc into dilute sulfuric acid. The acid reacts with the metal, generating a steady stream of rising bubbles. This releases a flammable byproduct, hydrogen gas. We pipe this invisible gas into a secondary container to prove it's there. To confirm we've actually captured hydrogen, we can trap the invisible gas inside a soap bubble and bring a burning candle close to it. The flame instantly ignites the trapped gas, combusting with a sharp, distinct pop. That micro-explosion is direct evidence of its volatile energy, hidden inside an acid, waiting to be unleashed when it meets the right material. Acids behave very differently depending on what they encounter. If you swap the solid metal for a metal carbonate, like everyday baking soda, the reaction changes completely. The mixture still violently bubbles, but it no longer creates flammable hydrogen. Instead, it produces carbon dioxide gas. We test for CO2 by piping gas through clear lime water. As it bubbles through, it reacts with the calcium, turning the beaker milky and opaque. So acids aggressively dismantle metals, and they quickly break down carbonates. But what happens if an acid collides directly with its exact opposite, a strong base? As seen here, the two highly reactive elements collide and essentially dismantle each other's extreme properties. Through a process called neutralization, the acid and the base combine to leave behind harmless salt and water. The same chemicals that can eat through zinc or burn human skin completely cancel each other out when mixed in the right proportions. This neutralization serves as a constant, practical balancing act that we rely on every single day to survive. Inside your stomach right now is a highly potent pool of hydrochloric acid. Your body requires this intense chemical environment to break down the meals you eat. But sometimes the stomach produces too much of it, causing a painful burn. To fix it, you swallow an antacid, like milk of magnesia. The antacid is a mild base that drops directly into your stomach to neutralize the excess acid and relieve the pain. You apply the exact same logic to a bug bite. When an ant or a bee stings you, they are injecting a localized dose of methanoic acid directly into your skin. By rubbing a mild household base like baking soda over the sting, you neutralize the venomous acid on contact, halting the burning sensation. We also utilize the carbon dioxide reaction in emergency situations. Mixing an acid with baking soda under pressure is the exact mechanism that powers soda acid fire extinguishers to choke out flames. And in the kitchen, baking powder contains both a mild acid and a base. When you add water and heat, they react to produce carbon dioxide bubbles inside your cake batter, forcing it to expand into a light, fluffy structure. Acids and bases are powerful, reactive forces. By understanding how they cancel each other out, we can safely harness their chemistry to heal our bodies, put out fires, and prepare our food.